Okay, in our next section, we're going to talk about the network address translation, or the NAT feature, that is mainly designed to change the layer 3 IP address field, whether we're changing the source addresses or the destination addresses. The router essentially is going to be editing the packet as it's moving between interfaces. And the most common application of this is that we want to hide our private addresses from the internet, where in the vast majority of cases, when you're routing with the internet, you're not going to be assigned a public address for every individual host that's in your network. A lot of the times we're going to be using what is defined by RFC 1918, or basically the private use addresses, where the private use addresses are going to be in Class A, the 10.0.0.0 through 10.255, 255, or in other words 10.0.0.0/8. The Class Bs are going to be from 172.16.0.0 through 172.31, 255, and Class C is the 192.168 address through 192, 168, 255, 255. Now, technically, you could choose any addresses you want for the assignment in your network, but the problem that you could run into is that if you choose someone else's public address and then assign it in your own internal network, if you happen to overlap some address that you're trying to reach on the internet, like let's say you open up your web browser and you go to www.google.com, and it resolves to an address you have already assigned internally, it's going to go to your internal host as opposed to going to your external host. Because the routers are always going to choose what is the closest path in the network, or whatever the shortest path is. So by using this RFC 1918 addresses, we're going to assume that these are not advertised out onto the internet anywhere. So each of the networks can basically use this as locally significant address space, or private use address space, as it's specifically defined. And in order for these hosts to then reach the internet, we need to change what the source addresses they're using. And that's what the network address translation feature is designed to solve. This could also be used in cases where two networks are merging, and we need to do essentially what's known as a double NAT translation, where both the source address and the destination address is on the same network. So we're trying to resolve where the subnets are overlapping. We could also change the destination addresses. And this is typically used when you have traffic coming in from the internet and you want to redirect it to an internal server like your web server or your mail server, but you don't have a full public address space that you allocate on a one-to-one basis. So sometimes this will be configured as a static one-to-one translation, or it could be configured as what is known as a port address translation, or a PAT. Where with port address translation, we're going to be including the layer 4 information, which is the TCP and the UDP port values, in order for us to share a single outside address or a single global address between multiple inside hosts. And sometimes this is called NAT overload. This is by far the most common scenario when you're connecting to your normal ISP, like at your home, where if you go to your DSL modem or you go to your cable modem, when you send traffic out, the router on your edge is going to be running NAT, and it's going to translate your internal addresses to some single address on the outside. Where the difference between the two of them, technically a NAT translation is 1-to-1, where a PAT translation, or a port address translation, is many-to-1. So we're trying to share the single public address on the outside with multiple devices on the inside network. And the way that we can do that is that the router who's doing the translation is going to maintain what's known as the network address translation, or the port address translation table, that it has this mapping of what are the TCP port values or UDP port values and how they correspond to the inside hosts. And we'll see that the reason we're able to do this is that when a TCP or UDP client goes to send traffic to a public server, they go through a negotiation that they choose one of the port values as the source or destination, depending on the application. And since the port value range is pretty large, it goes from 0 to 65535, it's unlikely that the combination of your IP source address, your IP destination address, your layer 4, so either your TCP or your UDP source port, and the layer 4 TCP or UDP destination port, it's very likely that very unlikely that the combination of all of these together is going to overlap between two individual hosts. So based on this, the router is going to keep track of when traffic leaves the network and then it comes back, who is it actually supposed to go to? And sometimes this is what we categorize our flows as, where the flow is going to be the IP source, the IP destination, plus the layer 4 information, the source port and destination port, and the protocol, whether we're using TCP or UDP. So in order to implement NAT, we need to understand some of the terms that the feature uses. First is we have what's known as the inside network or the inside zone. This is generally the addresses that we're trying to hide from the public network. And out of the inside zone, there's going to be two subdivisions, which are known as the inside local and the inside global, where the distinction is that if the addresses are inside, they're under your administration. If the addresses are outside, they're going to be under someone else's administration. So if we had a topology where we have some source A, that this is an end host, that's sending traffic onto the LAN, and eventually it gets to the edge router, and the edge router is trying to send this out to the internet, and then eventually it's coming out the other end to some service. Let's say that this is a web server. From router 1's perspective, the device that's performing the network address translation, we would then say that this portion is the inside network, and this portion is the outside network. So we're trying to translate or change these addresses as we're moving from the inside to the outside. The private address that this host is assigned would then be considered its inside local address, because it's locally significant to our inside network. This is what we're going to change to the inside global address, where the global address has global significance to the internet, or in other words, it's going to be a unique address. So most translations are going to be an inside local to an inside global. When the traffic ultimately reaches the destination, and they look at the source address is going to be this inside global value. Then we also have the outside zone, or the outside NAT. This is generally the addresses that are not under our administration. This is going to be the addresses we're trying to reach. Where the outside global ones are going to be the addresses from the perspective of A. That's going to be the address that it goes to get to the web server as. You could potentially have also an outside local. This would be in the case that they are also doing a network address translation, and you're translating in both directions. So typically the last one is only used when you are having overlapping subnets, and you're trying to get from subnet A on one side to subnet A all the way on the other side. And you have to have two translations. You're translating both the source and the destination on both sides. But in the vast majority of configurations for this, we're going to deal with just the association between the inside local and the inside global values. So here we have a minor change in the topology, where we still have the four routers that are running IP on the VLAN 2, the VLAN 1, VLAN 3, and VLAN 4. But now we have some router on the outside of our network that we ultimately want to get traffic from the Windows machine to be able to go down to router 3 and then get sent out to what we'll consider the wide area network, to whatever some public destinations are, like in the internet. So router 3 is going to be the one that's performing the network address translation. From 3's perspective, the links that are connecting to the Ethernet interfaces, this would be the inside. Then the serial WAN interface that's connecting to router 2, this would be the outside. And the design problem that we're running into is that on the inside of our network, we're using this private address space, the 192.168 space. So when packets go to router 2, it's not going to have a route back to these because no one on the internet is going to accept the routes 192.168 or the 10 network or the 172.16 to 31. So we essentially need to change our addresses to something they do have a route to and something that can be publicly routable on the internet. And that's what router 3 is going to be doing. It's going to be changing the inside local addresses, which are the 192.168s. They're going to be changing them to inside global addresses, which could either be the address that's assigned on our interface, or it could be some sort of pool that's assigned from our service provider. So first we'll look at the case where we're doing just the most basic translation, which is considered an overload to the interface. Then we'll look at some more advanced examples of this where we're using pools, and we could also do the translation in the reverse direction as well. Documentation-wise, this is going to be under those IP services that we were looking at before, where if you go down to the configuration guides, under iOS, the specific release, then the configuration guides. Since we're dealing with IP addresses, this is going to be part of the IP documentation, then addressing services and network address translation. Now there's a lot of advanced functionality you can do with the NAT process. There's cases where you may have multiple routers that are connecting to the internet and you want to translate to different pools depending if I'm sending my traffic to one provider versus another. Or maybe I have multiple routers at the edge that are trying to fix the case that if one of them fails, that the other one is going to take over. That's mainly what these type of topics here are going to be talking about. For the most basic functionality of NAT, it's going to be this first document, just configuring NAT for IP address conservation. Now, one thing that we didn't look at yet with the documentation is not only does it have general overviews about what the topics are, like what is NAT, why would you want to use it. We saw it has that list of what's the step-by-step configurations you need to do, so how to configure NAT. But then also towards the end of these documents, they're generally going to have specific examples that show you the final configuration of what network address translation would be, or the final configuration of what DHCP server would be. So a lot of times you can take these and change them around to meet whatever your specific design is. It's just kind of a basic template you can use for the syntax. But overall, most of the configuration is going to be done with the IPNAT command. This is how we decide what addresses are we matching to do the translation, and then what are we going to translate them to. Now, before we get to this portion of the actual translation, we need to make sure that everything up to layer 3 for routing is working. Because when the packets come in to router 3 and we do a translation, we need to make sure that when router 3 receives the return packets, it actually knows how to get back to the originating sources. So we need to assume that there's nothing wrong with the Ethernet LAN, there's nothing wrong with the IP addresses, the basic routing protocols. At this point, if we were to look at any of these routers, and let's say on router 1, if we look at the show IP route, we want to make sure that somehow we're learning the different subnets in the network. Where in this case we have EdgeRP running as one of the dynamic protocols. So if we were to go to our Windows machine here, I want to know that up to this point, can I at least get my traffic to router 3? And that's going to be the one who's performing the address translations. Okay, in the meantime, while that's, I think that server's rebooting, let's look at this from the perspective of the network itself. So from our previous configurations with the DHCP, router 2 is configured on this segment behind switch 1, and we can test it from behind here as well. So on router 2, if we look at the show IP route, we have, actually no, router 2 is down here for this example, so we can't do that. We'll look at this from the switch itself. So on switch 1, let's look at the show IP route. I have routes that should at least get me up to router 3. Now again, remember with IP routing, just because I know how to get there doesn't necessarily mean that they know how to get back to me, because they're two unrelated decisions. How I route to get to you and then how you route back to get to me. So one way that you can test, does a particular router have a route back to an individual network or an individual segment, is that when you send the traffic, if I were to ping this loopback we have on router 3, would be to change the source address of the segment you're trying to test, does router 3 have connectivity to? So I want to know, does router 3 have a route back to this VLAN 1 network? So on switch 1, I'm going to say that this is the source of where I'm sending the packets from. This means that switch 1 is generating its packets from 192.168.0.254, going to router 3. Up to this point, looks like everything is fine. So basic routing up to router 3 is fine. Between router 3 and router 2, we have a pretty basic configuration here of a serial interface. And we're going to get into some more of the specifics about this later. But basically, the only thing that we care about here is that we have just basic IP connectivity between router 2 and router 3. So router 2 can ping 3, but it doesn't have a route to any of the devices on the inside of that network. And ultimately, when we look at the show IP route of router 2, it shouldn't have those routes, because if router 2 is on the outside of the network, it's not going to know the internal private addressing of the internal network. So the 192.168s, these are going to stay on the inside. They're going to have to get translated to something else as they move to the outside. So now at least I know up to this point the routing should be working fine. Next thing we're going to do is define which addresses are we going to change when we move them from the inside to the outside network. And this is what the IP/NAT inside source command does. It says that as packets are received from the inside portion of my network, I want to change the source addresses. Which source addresses I'm going to change are going to be based on this criteria that I can match. It could be based on an access control list. It could be based on what's known as a route map, which is a more modular configuration of an access list, gives you more control over it. Or a static translation would be if I wanted to do a one-to-one mapping, like an internal web server, I want to give it a specific address on the outside. That would be a static translation. So here I'm going to say, based on some access list that I'm matching traffic on, this is what's going to control which addresses will be translated. And specifically, I'm going to create an access list that says to match or permit traffic that is sourced from addresses in the 192.168.0.0 network, 192.168, 1.0, 2.0, and 3.0. So essentially, these are my internal subnets that I'm trying to change their addresses from. Next, I have the NAT command, IP/NAT inside source. Where is the traffic coming from? It's coming from addresses in access list 1. Then I can either specify to change their addresses to what's already on my interface, or to some pool of addresses that have been assigned to me by the service provider. So whether this is space that they own or space that you've publicly registered for, you can have cases where the link between you and the service provider may not be routable itself. Like you could have the case where this is 10.0.0.0/24. And this is used just to get your traffic to them, where really your public addresses may be something like 200.0.0.0/24. But in this first example, we're just going to change the source addresses to what router 3 has assigned on this serial link. We'll say change them to the interface serial 1/1. And in order to do a port address translation, you would need to add the overload command here. This is what is going to allow me to do the many to one, where there's more than one host on the inside. So this tells it to look at the TCP and UDP port values, not just based on the layer 3 IP addresses. The next thing I need to specify is what interface is the traffic coming from and what interface is the traffic going to. Where on router 3, there's 3 interfaces, the 2 LAN interfaces and the 1 serial or WAN interface. Fast Ethernet 0/0, this is going to be the inside, as will Fast Ethernet 0/1. Serial 1/1, this is connecting to the outside network. So our translation should happen when packets go this way or when packets go that way. So what interface is it coming from? What interface is it going to? This is what we specify at the interface itself as either the IPNAT inside or the IPNAT outside interface. So the serial interface here will be the outside. The LAN interfaces are going to be the inside. If we look at the show run result, we're saying that anything that comes in from this interface and it goes to an interface that is outside, then we'll do a translation. It also means that if the packets are going between 2 inside interfaces, there will not be a translation. So only when we're going from inside to outside or from outside back to inside. If you have 2 outside interfaces, those won't translate together, or if you have multiple inside interfaces, likewise, those won't. Next thing we're going to look at is the show IPNAT translations. This is what verifies the translation table, or essentially what are the changes that router 3 made in the packets. Now at this point, the devices on the inside network, they don't actually have a route to router 2. So in most typical designs for connecting to the internet, what the edge router here, router 3, would be doing is advertising a default route, or 0000/0, into the dynamic routing protocol. So if someone wants to reach the 192.168.2.0 network, they would have a specific route for that. They would know to go either this way or maybe this direction. But for anything else that I don't have a match for, I'm going to fall back to this default route, and then that's going to shove my traffic out towards the internet or out towards the service provider. So on router 3, I'm going to add some changes to the EDGRP configuration, to the dynamic routing. I'm going to say that to get to 0000, so IP route all zeros, go out this serial link. Then under the EDGRP process, I'm going to advertise this static route into the dynamic protocol. And the way I do this is through redistribution. I'll say redistribute that static route. Then I need to give it some metric value. So when EDGRP does its calculation on this, it knows what is the bandwidth value, what is the delay value, what is the load, because that's ultimately how it calculates its composite metric and then figures out how you would route to this path. So it doesn't really matter what this is, I just have to give it some value. So the bandwidth, I'll say this is 10 or 100,000 kilobits per second. That would be 100 megabits per second. Maybe the delay is 100. The reliability is 100%. The load is 1%. And the MTU of IP packets is typically 1,500 bytes. So I could theoretically put all ones there or just any arbitrary values, but it has to be something. Otherwise, it's not going to be able to be advertised into EIGRP. If we look at the result of this on switch 1 or on router 1 or router 5, we should see that now, along with their other EIGRP learned routes, we now have this external route that is the default. Now, since the router is still making its decision based on the longest match, packets that are going to anything in 192.168.2 or 192.168.3, they're going to follow these paths. Only if I don't have a more specific match to the destination, then I'm going to go to the default route. So now let's test this out. What we should ultimately see is that if we were to do a ping or we were to do a telnet to router 2, that when the traffic goes out, router 2 is going to think this is coming from this address, which on router 3 I have it assigned as the 100.0.0.3 address. So let's go to switch 1 and I'm going to telnet to router 2, to 100.0.0.2. Again, this means that router 2 has telnet enabled, but we didn't configure a password yet. So what do I need to change here on router 2? I could either go under the VTY line for virtual terminals. This is for telnet or SSH. And either I could say, give it a password, like use the password Cisco there, or I could tell it to check for local usernames. If I were to say no login, it would just allow them in without asking for a password. In this case, we'll say password Cisco. So now when the user telnet's there, if I were to look at the show users, this is going to show me the address that router 2 thinks I'm coming from, which in this case is 100.0.0.3, which is that outside interface of router 3. Where in reality the traffic is coming from this interface because that's what switch 1 would use to route to that neighbor. So if the telnet packets are going in this direction, whatever the outgoing interface is that switch 1 has, that would be the source of the packets. So in this case it would be 192.168.1.254. But router 2 is saying they're coming from 100.0.0.3. This means that when we look at the original IP packet, where it would have the IP source of 192.168.1.254, it has the IP destination of 100.0.0.2. It's running TCP because we're doing a telnet. The TCP source port is going to be some random value. The TCP destination port for telnet is what? Is 23. But then it gets to router 3 and it goes through the NAT process. Router 3 is now changing the source. It's changing it to 100.0.0.3. It's not changing the destination. It's still 100.0.0.2. It's not changing the destination because router 2 is the one who's listening at this port value. But if we look at the comparison between what the originator of the traffic, which was switch 1, chose as this number, you may see that the NAT device is going to change this. Sometimes it'll stay the same, sometimes it'll change. It depends on how many translations that you have. But on router 3, if we were to look at the show IP NAT translations, it says that traffic came in from this source. This was the address that was on our inside network, and this is locally significant to us. This is the private address. It was going to this address, 100.0.0.2, and it was going to port 23. The inside host was requesting port number 52.429. So basically, this is a random value that they negotiate. I changed my translation so that there's a new source address, but the port value changed the same. Or port value was maintained between the two of them. If we were to theoretically have tens of thousands or hundreds of thousands of translations, sometimes someone else will end up with this port number, and in that case, router 3 is just going to change it to a different value here. But as long as the combination of all 4 of these fields ends up to be unique, when the traffic comes back in, it knows how to retranslate the traffic. So as we're going from the inside to the outside, we're changing the source address. But as we're coming from the outside back inside, we're changing the destination. Because when router 2 does its reply, it's sending the packets to 100.0.0.3. So we're taking this and changing it to this value. Then when switch 1 gets the packets back in, from its perspective, it's traffic that is going to its inside address. We would also see this if we went to router 2 and looked at the debug IP ICMP. Then from the inside network, let's say from router 1, we do a ping to router 2's address. And we do the same thing from a couple of inside hosts. Let's say we do it from router 1, we do it from router 5, and from switch 1. When router 2 receives all of these packets, even though they came from 3 unique sources, from their perspective, or from router 2's perspective, it's really all coming from this address, 100.0.0.3. Then when router 3 gets the replies, it's going to change them back based on these mappings. So it says that switch 1 did a ping to router 2, change it to this value. But this number here is allowing router 3 to have multiple connections at the same time that are sharing the source address. So this is what our port address translation, or the NAT overload, is allowing us to do. So let's say we now want to do this not only to this specific address, so not to the outside address, but maybe there's a pool of addresses that the service provider has given us. Let's say that this is the range of addresses that go from 100.0.0.64 to 100.0.0.96 or 95. So this is some smaller range that the service provider is allocating to us. When my traffic comes from the inside out, I'm going to translate it to somewhere in this range. This is what router 3 would then define as the IP NAT pool. I'll say this is my public addresses. So the pool has a name. The pool starts at 100.0.0.64, and it goes through 100.0.0.95. Then the subnet mask, or the prefix length, would tell router 3 when traffic comes back in what is part of my pool or what is not. So it's basically just like the subnet mask of the network that you're translating to. So I would say the net mask there. this case, I'll say it's /24. So now when I do my translation, I'm going to remove the previous statement. So we're not doing the many to one translation. No IPNet inside sourceless one. We'll say instead we're going to translate to a pool. And the pool's name is public address. From router 2, we're still looking at the debug IP ICMP. When packets now come from the inside and go out to router 2, so from router 1, from switch 1, and from router 5, we'll see that router 3 is now doing a one-to-one translation, where each of these sessions is allocated a new unique address from the pool, because I didn't tell it to do a port address translation. This means that when we look at router 3's translation table, the show IP NAT translations, it doesn't correlate the port value with these. It just says that switch 1's address got translated to the .65. And router 5's address got translated to 66. Router 1's address got translated to 64. The problem with this, though, is that if you run out of unique addresses, then devices on the inside won't be able to send their traffic out. So this is technically a network address translation. This is a one-to-one. It's not very common to do this, though, because you normally don't have enough public addresses to equal the inside hosts. But where this does become useful, if there's a specific server on your inside that you want to give them a public address. So let's say that we have on switch 1, we want this to be able to be accessible from the outside. So there's some sort of service that it's running. Let's say it's running its web server process. And the web server is listening on TCP port 80. If we were to go to switch 1 and say IP HTTP server, this is going to turn the process on, so now it's listening at port 80. Since web browsing, or HTTP, runs on top of TCP as the layer 4 transport, one basic verification and troubleshooting tool that you can use is telnet and change the port number that you're going to. So let's say I want to know that from router 1, can I get to the web service of switch 1? Normally, telnet is used for management of the devices. Like if I telnet to this address, normally this is going to switch 1's command line. So on switch 1, under the VTY lines, I'll say no login. Now when router 1 telnet's there, it gets to the exec process, or the command line of switch 1. But basically, since the only thing telnet is doing is opening a TCP session and then sending characters back and forth, you can use it as a basic test of the layer 4 reachability in the network. That if I were to telnet to that address, but then change the destination port to HTTP, or is it www? www, they say. I now know that I can connect to the web server. Now, I can't actually use it if I knew the raw syntax of HTTP. You could actually type it in, and then you'd be able to download a web page. But based on this response, we can tell at least that the web server is listening for our connection. So what we're going to do now on router 3 is assign switch 1 a unique address on the outside. Let's say 10.0.0.254. And just for traffic going to this address, or not 10, I should say 100. 100.0.0.254. 254. We're going to do a one-to-one translation in the reverse direction. Where 100.0.0.254, this is going to map on the inside to 192.168.1.254. And this is what the IPNAT inside source static command is used for. We can either do this on a per port basis or just a per address basis, where the inside local address, this is which one that we need to match? The 100 address or the 192 address? It's the 192 address because that's the one that's locally significant to us. It's not the routable address. So the inside local would be 192.168.1.254. The inside global, that's the one that the global internet table has reachability to. So that's the public address. We'll say 100.0.0.254. Non-static entry already exists. What this means is I need to delete the old entries to free up some of the mappings. Because there's an error where the mappings they're overwriting each other and it doesn't allow you to do that. So I need to say clear IPNAT translations. Star, that'll delete all of them. But now if we were to go to router 2 and telnet to 100.0.0.254, that maps directly to switch 1 on the inside. If I was to ping 100.0.0.254, this address that I'm actually reaching is switch 1. And on switch 1, if we said debug IP ICMP, I would see these pings making it directly to there. So it's replying to router 2, but it thinks that the packets were really going to 192.168.1.254. If we were to telnet to port 80, that's going to be the web service listening. Now the disadvantage of this configuration is probably going to be what though? If this is your internal web server, it means that every single service the application is running is going to be reachable from the outside. Like it could be like it's Windows file sharing, or it could be some other service that's vulnerable to a security flaw. So a lot of times you don't do this. When you do the translation, you typically pick what are the services that you want to send from the outside to the inside, and then map just those ones. That's what the IPNAT inside source static TCP or UDP would allow us to do. To say do a static port address translation. So when traffic comes in, but it has to be going to port 80, then I'll do the forwarding. And this is what those small office or home office routers call port forwarding, where you're doing a static port translation or a static PAT from the outside to the inside. So on router 3, let's remove the static entry. Instead, I'm going to change this with the similar syntax, IPNAT inside source static, but I'm going to add the keyword TCP. The local address is still the 192.168, but now I get to choose what port do I want to send inside. This is going to be the port that they are listening at. So let's say it's port 23 for telnet. The global address I'm translating to, it could be something on my interface, or it could be something that's part of a pool. Then I also have the choice of what is the global port. So I could match them one-to-one, where when router 2 telnets to 100.0.0.254 at port 23, it's going to really change that to 192.168.1.254 at port 23. So now if I telnet to that address, we should see it go through, which it does. But you can technically also change these to whatever arbitrary values that you want. So I could say on the outside, don't listen at port 23. Maybe I'm going to listen at 60,023. So now when router 2 goes to port 23, that's the default, it's not listening for this one. Instead, what it's listening for is 60,023. But from the inside host perspective, switch 1, it doesn't know that this translation is going on. It's completely transparent to it. The only one that knows is router 3, because it's the one that keeps the NAT translation table. It says that if a packet comes from 192.168.1.254 and the source port is 23, change the source port to 60,023. Which also means the same thing in the reverse direction, that if traffic comes to this address going to 60,023, change it to this new destination with the new destination port. So it automatically works both directions, from the inside out and from the outside in. Okay, when it's a static translation. When it's the dynamic translation, which is the very first example we did, this one here is only inside to outside. It means that you cannot send traffic from the internet into the private network without the traffic already have originating from the inside. So NAT is also considered a security technique, because if I were to do this, and remove my previous static translation. So on router 3, let's say show run include NAT. This is doing the inside to outside port translation. On switch 1, if I ping 100.0.0.2, this is getting port translated. Or if I were to telnet to 100.0.0.2. When I show users, it's going to look like it's coming from 100.0.0.3. But if router 2 were to telnet in the reverse direction, if router 2 were to telnet to 100.0.0.3, this doesn't get translated back to switch 1. So from the inside out, when we look at show IP NAT translations, this inside host can start a session going to 100.0.0.2, and we're going to change it to this. But when this host tries to start a session to this address, it doesn't map to this one. So it stops your traffic from coming from the internet inside your network without you asking for it in the first place. Okay, let's see on the Windows machine now, if we look at this from the SDM, the web interface, this should be under the network address translation section here under configure. If we go this, so under the configure tab down to NAT and edit NAT configuration, so I already have mine built. If we were to edit this, it says look for traffic matched in access list 1. As traffic moves from the inside to the outside, where the inside interfaces are the fast Ethernets, then I'm going to do a translation directly to the interface address that's on serial 1/1. So you can accomplish the same thing here, it's just that it's putting this command line syntax in for you automatically. And then if we were to look at the There should be under monitoring, there should be the NAT table. Traffic status, no, that's net flow. And again, the problem is you can't do all of the same verifications from the web interface. But probably under somewhere it's going to show you here what the translations are.